to drop that term when we do this check. And do this check if the drain voltage greater than or equal to the gate voltage minus the threshold. Now we still need the source voltage, but to do this check, we do not need, we can make this check without the source voltage. So the drain voltage is 1 volt, that greater than the gate voltage of 0 minus the threshold of 2 volts. So 0 minus 2, and that gives 1 volt is greater than minus 2, so the Mosfet must be in saturation in order to meet the drain voltage requirement. Now, establishing that, now we can go back to our table and pick the equation for the NMOS in saturation. And we need U sub n COX, and we need W over L. So we're going to have to assume the problem is giving that information. So the drain current was given as 0.4 milliampere, and C sub U sub n COX, we'll go back and check it. U sub n COX is 20 microamps per volt squared. So there's 20 times 10 to the minus 6, and then the milliamp is 0.4 times 10 to the minus 3. And since we do not have the source voltage, the only unknown in this equation here is the gate to source voltage in this equation. So go ahead and solve this equation for the gate to source voltage. Solving it, we have to watch those exponents because they can, if not entered correctly, you can get errors. Over 10 is 40, and 1/2 times 40 is 20, and we have 20 times 10 to the minus 6, and the milliamp, the 10 to the minus 3 will cancel. So this term, what does this term become?
Point 0.4 times 10 to the negative 3 as well.
So that's 0.4 times 10 to the negative 3. That's the same term on this side. So we can cancel those both out on both sides of the equation and get 1 here. So we should get 0.4, we should get 1 is equal to V sub gate to source minus 2 squared because it canceled. And this, the note here is just noting that the currents are here are in milliamps, even though you don't always show the milliamp scale. Advise to always use the full exponents rather than try to take the shortcut. Some of these are taking the shortcut, but they're not leaving the the real exponents here. So this equation, we have use of in COX, we have W over L, and one more step at the top here. So here's the intermediate step here. 0.4 times 10 to minus 3 is equal to 0.5 times 20 times 10 to the minus 6 times 40. And that term turns out to be 0.4 times 10 to the minus 3. That cancels here. And we're left with d sub gate to source minus 2 squared equal to 1. So what are the solutions for this equation?
Plus 3, plus 1, or 3 volts or 1 volt is equal to the
So if we solve d gate to source minus 2, we came close to a quadratic here. However, we ended up with something just set in its place with plus or minus 1. So the two solutions, the gate source voltage can be 1 volt, or the gate to source voltage can be 3 volts. So how do we determine which one is correct? Or the better alternative? Threshold turn on is 2 volts. And one of our equations indicates that in order for MOS to be saturation or to be turned on, the gate to source voltage must be greater than the threshold voltage. So which of these two we can decide?
I see. That must be 3 volts.
This is greater than 2 volts.
3 volts?
3 volts. This is 3 volts. 3 volts is greater than 2 volts. And if we had decided it was 1 volt, the note at the top is that that would be a false outcome. If the gate to source is 1 volt, that's less than the turn on of 2 volts, so the Mosfet would be in the cutoff mode. Now that might end the problem pretty quickly, but it also produces a large error in the result, not being clear on which one of the gating source voltage will keep the Mosfet in saturation. So the gate to source then is equal to 3 volts. We decided that's the best result. And the drain current was given to be 0.4 milliamperes. So we want a gate to source voltage of 3 volts. We want a drain current of 0.4 milliamperes. So at the lower part, the gate to source is either gate voltage minus the source voltage. The gate voltage is 0 minus d sub s is equal to 3 volts. Get that from up here. This is what we saw for the gate to source. And now we're going to solve for the source voltage is minus 3 volts. So we have minus 3 volts on the source. And it makes sense because this is 0 and then the source is minus 3, so the gate to source would be 0 minus the minus 3 or 3 volts. So we're trying to keep the logic in our results so we can find out when we're actually moving away from the saturation part here. So we have our source voltage is minus 3 volts. We now have all the voltages. We have drain voltage, source voltage, and gate voltage. We have drain current and source current. So now the remainder is just Ohm's law. So what value of this resistor will allow 0.4 milliamperes, so the source voltage is -3, and we be aware of the polarities in here, -3, minus or -5. We don't want to get a negative resistance over here, because we didn't follow the polarity. So that's over 0.4 milliamp. Again, the author doesn't write out the milliamperes in here. There's 5K ohms. The drain resistor is 5 volts minus the drain voltage divided by the drain current, 0.4 milliamperes, and that's 10K ohms, and we're done. So this problem basically avoided a quadratic equation because it basically gave too much information to start with. Now, other problems are going to not give so much information, so you're definitely going to be moving towards some more math analysis here. So, the quadratic equation, we didn't come across that when we were working with BJT, that note is just saying that. When we have a quadratic equation, you do one good solution, but the false solution might not be obvious until we work on the math. If we have all the Mosfet node voltages, then determining which mode the Mosfet in is trivial. And that's what we went over in our last session, is we were given a group of MOSFETs and all the node voltages were given, and our job was just to determine what the mode it was in. So now we're at a point where the node voltages are not going to be given, and we have to solve for them, and since they're unknown, we're definitely going to have to do more math in order to solve for those different voltages. So this example here, and it's a MOSFET, threshold voltage is 1 volt, and this note says Kn prime or Kp prime. Either one is 0.1 milliamp per volt squared. If it's a PMOS, the threshold is -1 volt. W over L is 10, and then lambda is equal to 0. Case of N. What is that equal to? I mean, it's equal to 0.1 milliamp per volt squared, but what are the parameters to get that?
It's the permeability times the capacitance of the oxide.
The permeability times the oxide extent. So be aware that case of N could be given as mu sub N times C oxide. So we want the drain voltage to be -2 volts, and we want the drain current to be 0.2 milliamperes. So, and the gate is grounded, so the MOSFET in saturation, or is it in triode mode? Is the drain voltage greater than or equal to the gate voltage minus the threshold?
It is.
So
No.
is -2 volts greater than 0 volts on the gate minus 1 volt threshold, which is -1, and the -2 is not greater than or equal to -1. That means this device is not in saturation, it's in triode mode. Now, if we didn't catch this from the start, we'd probably be trying to solve one drain current equation and using up probably 10 to 15 minutes of unnecessary effort because we didn't really study the schematic and the information that was given. So this problem gives all the information to make a quick decision about saturation or triode. And because saturation didn't work, you might say, what about cutoff mode? So the gate voltage is 0, and it says here the source voltage is equal to minus 5 volts. Where do we get this? No, the source is minus 5 volts.
From the bias.
If it's in cutoff,
There's no
the
current.
source is
There's no
minus,
current.
Yeah.
there's no current, so this is minus 5 volts. And then we check, is the gate source greater than VT? Is 0 minus or minus 5 greater than 1 volt? So 5 volts greater than 1 volt, and this is false, so it's definitely not in cutoff mode. The remaining mode is the triode mode. And the advice here is to definitely don't shy away from the math in a problem like this. This problem, because it's in triode mode, it's going to have a square term somewhere, and it's going to produce a quadratic equation. So, in the result here, because we have simplified this in triode mode, our table, we now go back to our table, and we get our drain current for the triode mode. Now, this point over here is going to leave this for your homework assignment. The drain current is given as 0.2 milliamperes here. So this equation is reduced to this equation over here. Now, whatever, and I sort of wrote up here what happened to the coefficient Kn prime W over L is here. It's 0.2 times 10 to the minus 3 is equal to 0.1 times 10 to the minus 3 times 10. And that basically is going to divide out in 0.2. So that's why this Kn prime W over L term is still in there, but this math shows that it divides out to 0.2. So now you basically have to take this part and now separate it out into the various parts of the equation. These first two parts, minus V sub S minus 1. The gate is at 0 volts, so minus V sub S, 0 minus V sub S, that's the gate to source. The drain to source, the drain voltage is given as minus 2, and then that's minus 2 minus V sub S, and then minus the 1/2 the drain to source minus 2 minus V sub S. Now you have to manipulate this equation, and this is the author showing the different parts of manipulating that equation. Here, eventually we get a quadratic result over here equal to 0, and then once we have that result, we take our quadratic formula here. Solve for two roots, minus 1 plus or minus 1.183 on the roots here. And if the source voltage is minus 1 minus 1.183, that means the source is 0.183. And the gate to source would be 0 minus 0 minus 0.183. And that means the gate to source voltage is actually less than 0. And then that's a false result. And if this source voltage is minus 2.183 volts, then gate to source then is 0 minus or minus 2. It's going to be 2.1, and that's just barely above the threshold of 2 volts. Of one, as well as above 1 volt. So it gives an little check mark, means that this is the correct result. So once we have these numbers, the original question was find the drain resistor and the source resistor. And again, this is just Ohm's law. Once we get through this, solving this quadratic equation, it just becomes Ohm's law here. The drain resistor is the battery minus the drain voltage. In actual reality, we could have solved this one before we even solved the problem, because enough information was given. And then the source voltage, the source is minus 2.183 minus a minus 5 over 0.2 milliamp. I believe that's 14 k. So I definitely recommend go through this problem and practice the quadratic equation part of it, and then practice the detail and find out where any errors start to come up. Most of the errors in problems like this are dealing with this Kn prime WL number here.
And when the VDS is negative,
What's the question?
VDS is like one is negative.
It says here that from this expression here, the unknown is V sub S. So when we sort out the equation, we want to get one unknown. And now eventually we get V sub S has two results.
When you choose the negative value, negative 2, you say that the other one is wrong because VDS is
If
negative.
one of them is minus, you have minus 1 plus 1.183, and that gives 0.183 volts. However, if we have 0.183 volts on the source, the gate is at 0, so we have 0 minus 0.183. 0.183 is a gate to source voltage less than 0, and the threshold is equal to 1 volt. So that means the device is cut off. So that's not the right one. If it goes to this one, minus 1 minus 1.183, the source voltage is minus 2.183, and that means the gate to source is now 0 minus a minus 2 point, which is a positive number, and is greater than the threshold of 1 volt. And that checks off as the most appropriate result. So go through it on paper, and another example here is NMOS transistor, and the specs are given. Threshold is 2 volts. NUSA NCOX is 20 microamps. Volt square. Length is 10 micrometers. Width is 100 micrometers. And find the resistor R, so the drain current is 4 milliamps. Now by inspecting the circuit, we find the drain is connected to the gate. The drain is connected to the gate. So is the gate to source voltage equal to the drain to source voltage? And we're trying to simplify the problem before we.
Yes.
So we find that the gate source is the same as the drain source.
Yes.
We get that from the schematic. So our equation gain is connected to the gate, so that voltage is 0. So the equation is the drain to source greater than or equal to the gate to source minus the threshold. We can reduce that to the drain voltage greater than or equal to the gate voltage minus the threshold. And this numbers here, they cancel out, so it is 0 greater than or equal to minus V sub T. And it says yes. So this transistor is always in saturation. So this is called saturation. Saturation by structure, the way it's actually designed. It's always in saturation. So with the drainer gate equal to 0, that's where we get this term saturation by structure. So we want to recognize that schematic. Because it's in saturation, we go to our table or our formula sheet and we find the correct proper equation. And the drain current is given as 0.4 milliampere. You're back in a mode where the gate to source voltage, we need something to put in here for the gate to source voltage. And we notice though, there's only one unknown in this equation here, and that's the gate to the source. So there's no need to break up this into gate and source voltages. We just solve for, so this is another homework assignment, is go through the quadratic equation that comes out of it. One of the results, gate to source 1 is 0, and the second one, gate to source, is equal to 4 volts. And which of these is the false result? And we have our table, so we go to our table.
Gate is A plus B. Correct?
From our table,
Gate to source must be 0.
the gate to source must be greater than the threshold.
Alright.
So,
Must be 4.
so from these results, only 4 is greater than the threshold. So the false result was the gate to source. If we decided this was the result, the transistor would be in cutoff, wouldn't be in saturation. So gate to source 4 volts is the correct one. With that, gate to source is V sub gate minus V sub source. The source is at 0 volts. And that number comes out to be 4 volts. So V sub gate is equal to V sub drain, which is equal to 4 volts. And now we can solve for the resistance. On the battery, 10 volts minus the 4 volts here divided by the drain current is 15 k ohms. So a problem like this in terms of resolving it, we came across that the gate, the unknown here was the gate, the source voltage, but it's only one unknown. So we do not have to get a quadratic equation to solve it. So, when we were studying BJT, we came across a circuit similar to that Mosfet, where the base collector voltage was equal to 0. We had a BJT, and this was the collector, and the base. And then we took a wire and connected the base to the collector. When we did that, that created a diode in there when we did that. So that's a saturation by structure for BJT. That's one of the circuits that we studied. Another example here, on the NMOS enhancement device, and we notice here the gate is tied to battery, and the source is tied to ground. So two of the voltages are known. The gate voltage is 5 volts, the source is equal to 0 volts. So the gate is equal to the battery VDD. The threshold is 1 volt, turn on Kn prime W over L is 1 milliamp per volt squared. And this term includes the W over L. And what should this resistance be to get the drain voltage equal to 0.1 volts? Now that doesn't really say is it in saturation with triode here. But having a drain voltage that low is kind of a hint about something, how the circuit would operate. So source voltage is equal to 0, it's connected to ground. So the gate to source is the battery minus the source voltage, which is 5 volts minus 0 is equal to 5 volts. We want the drain voltage either 0.1 volts, or we want the drain to source to be equal to 0.1 volts. This term here, drain to source is 0.1, it should be obvious if the drain is at 0.1 volts. So we have the drain voltage, we have the source voltage, and we have the gate voltage. So now we can make a check. If we assume saturation for an NMOS enhancement, is the drain to source voltage greater than or equal to the gate to source minus the threshold, and since the source is common, we can change it to the drain voltage greater than or equal to the gate voltage minus the threshold. The drain voltage is given as 0.1 volt. Is that greater than or equal to the gate 5 minus the threshold 1, which is 4 volts. And this is false. So the transistor must be in the triode mode. So now we have to change our conclusion because we found a contradiction. The note at the lower part says we might have suspected triode mode because of the low drain voltage here. It's one that's very experienced working with Mosfet would probably catch on to that. You have very low drain to source voltage, and Mosfet is operating very close. It's operating in the triode mode. And remember the curve of the Mosfet, something like this. So a drain to source voltage of 0.1 would put drain to source here. And then we had a cutoff for triode and saturation here. So that's kind of giving a hint that the transistor is probably operating in a triode. That's kind of recalling the shape of this curve for the device. Now, the idea of triode by structure, this device is not in triode by structure. And a note here, if we had declared the drain voltage to be 4.5 volts, then we would have checked is the drain voltage greater than the gate voltage minus the threshold. Is 4.5 greater than or equal to the gate 5 volts minus 1 volt, which is 4 volts, and this is false. So this circuit would be in saturation. And now you're ready to solve it for that. Now, because this circuit is in triode mode, our formula sheet, we have our formula sheet, and this is our equation for an NMOS enhancement transistor in triode mode. And examining the equation, we're going to find out where are the unknowns in the equation. So, what is the gate to the source voltage? What is the gate to source voltage?
source, 5
5
volts.
5 minus 0, 5 volts, that gives us this number. The threshold is 1 volt, because we have this number. The drain voltage was given as 0.1 volts, so the drain to source is 0.1 minus 0, that's equal to 0.1. Then minus 1/2 times the 0.1 squared, and that gives 0.01. And we come to not having to use a quadratic equation. The drain current is 0.395 milliamperes. And now since we have this current here, we can use Ohm's law to solve for that resistor RZ. 5 volts minus 0.1 divided by 0.395 milliamperes, you get 12.4 kiloohms. Now this, when Mosfet is operating in triode mode, it's not useful as an amplifier. However, it does have use as a voltage controlled resistor. And if we calculate the drain to source resistance under this channel for this triode mode, it's equal to the drain to source of 0.1 over 0.395 milliamperes, 253 ohms. So if we wanted a MOSFET to control, say, an audio volume knob, and that's hidden behind the console, the stereo, that button could be tied into a MOSFET, and all it's doing is adjusting the drain voltage and changing the resistance that the audio has to pass through as it goes through the MOSFET. So that's called a variable resistor or potentiometer. And that way a MOSFET can be used to act as a resistive switch or variable attenuator. When MOSFETs are used like that, on a circuit symbol, instead of a MOSFET, what the symbol will show is something like this. And that means this device is a variable, it's a MOSFET, but it's a variable resistor. That's what it's being used at. So there are applications for triode mode MOSFET. Now these comments, this note is saying that these designs up to this point were fairly straightforward. And, the author here would actually call them simple designs. So the reason they're called simple is because most of the information to determine the mode the transistor is in was essentially given right here. And you just needed to be slightly organized. You needed to pay attention to the problem. You don't want to turn a MOSFET problem, a simple one, into a major half-hour or 45-minute problem. So the problem appears to be a simple design. It's just a matter of organizing the information. Now, following that is examples where the information is not completely given, and now we basically have to do some more analysis to uncover what's happening. So we do the same, we assume a mode, and we follow the assumption. If we find a contradiction, then we switch over to the other mode. If we assume saturation and it's false, then we go back and solve it in triode mode. So this is a MOSFET, an NMOS enhancement MOSFET, and the circuit is already designed. The drain and source resistors are given, and also the two gate resistors. So this question is going to ask, what's the drain current? What's the gate voltage? What's the drain voltage? And what is the threshold of 1 volt, and the coefficient Km prime delta over L is 1 milliamp per volt squared. Whether it's trial mode or saturation, we still use the same Mosfet parameter. From DC analysis, the gate voltage is 0. The two resistors, RG1 and RG2, form a voltage divider. So gate voltage from the map at the base is 10 volts times the parallel of those two resistors will equal 5 volts. And the lower part, the drain current is unknown, and we need to find the drain voltage and also the source voltage. And once we get those, we can study which mode the Mosfet is operating in. And then justify the assumptions. So we'll start with saturation mode. So at the bottom here, we'll take our saturation equation, which is here, and the unknown in here is the gate to source voltage. Even though we have the gate voltage, we don't have any results for the source voltage. So we want to manipulate this equation to try to get it into something with a single unknown on it. So this is the modified equation. Here, we take the gate to source, and we modify it into V sub G minus V sub S minus V sub T squared. So that's pretty simple. And the third variation, the source. Where do we get this number, this parameter from?
It'll be the current flowing through the resistor. It's just on slot.
The current, the voltage drop is equal to the source voltage. I sub D flows through the R sub S, so V sub S is I sub D times R sub S. So in this form, we have I sub D here, and we have I sub D on the left side of the equation. So it's a single unknown. We also have a square term in here, which brings up the likelihood of a quadratic equation resulting. But at least we change this equation from gate to source into something that just has the drain current on it. So the source voltage is the source resistance times the drain current, and this is it's actually 6K, 6 times 10 to the 3 IV. How the author here is leaving off the kilo units. You just understand that I sub D will be a milliamp here when you solve it. And there's just a note here that on the exam, we want to avoid writing an equation like that. You're going to put 6 times 10 cubed so that we can follow the exponent. You want to avoid this kind of shorthand. The shorthand in grading has to be interpreted. So you want to avoid interpretation of your work. You want to define exactly what you mean in your result. So if the source voltage is equal to voltage and ID is milliamp, again this is taking a shorthand cut. This actually, what happens when we do this is that we avoid some very large coefficients in the quadratic equation. So that's what the author is doing here, trying to avoid 100,000 or even million dividing by this milliamp here, and that's going to help reduce the coefficients on a possible quadratic equation. In your homework 2 assignment, the problem that we went over for the NMOS device, you want to avoid doing this. And it turned out when you do that, you'll probably end up with some very large coefficients for the quadratic equation. It just means you have to be more accurate in using your calculator to solve quadratic equation with very large numbers. So we'll use the shortcut method here. I'm sure you're going to review this problem for homework just in case it appears on the final exam. It won't be a strange problem that you have not come across before. So we'll stay with the author's kind of more convenient mode of the math. So the drain voltage is the battery VDD minus RD I sub D. And again, RD is 6 K ohm, so we're keeping that 6 instead of putting the K ohm. The K ohm cancels with the milliamp here, which also, so major shorthand is okay in this problem. So we'll need the drain voltage to verify saturation later. Now the top here, the source voltage is RSID, and the 6K times I sub D in milliamperes. Now you'll need to what you're doing in your homework is you'll take this equation here, you take this equation, and you convert it to this equation. Right here. And then once we basically, this form of the equation has I sub D as the only unknown. So once you get it in this form, now basically multiply the two parts and get this quadratic equation. I'm checking to find out if there's an error in one of these numbers may be off by one whole number. The 25 might actually be a 26, but you'll have to discover that when you solve this problem. Now, if you're this term 1 here, the question of where did a 1 come from? K prime W over L is 1 milliamp per volt squared. So in this result here, I sub D is in milliamp. This is 1 milliamp here. And then over here, this term is going to be in milliamp here. So all of the milliamps cancel when we do that. Now, when you solve this problem, as I said, for the problem like this on the exam, you want to write, and also for homework 2, you want to write in the full coefficients in milliamperes and K ohm. When we do that, the coefficients on this equation are going to be multiplied maybe by 10 cubed or so. We're going to have some large numbers, but the large numbers, the quadratic equation still works. So part of your homework for this problem is you actually have 3 homework assignments so far. You have the structure, saturation by structure, And we have the NMOS that appeared to be in saturation, but was actually in triode. And then now we have this version, which results in this equation that we have here. So go ahead and solve this equation for the quadratic roots.
0.8 and 0.5.
You're getting that from the quadratic. Now in the final exam, calculator will not be of much use in the final exam. And that's because if you're solving a quadratic equation, you must show every step in solving. If you solve a quadratic equation, the calculator gives you numbers, that's 0 points on that problem. You're not going to 0 out of 25. The reason you got 0 points is because you solved the problem, not the calculator. So mathematically, quadratics, you definitely want to practice it. This is a good problem to practice it on. So that's what I said. Now go ahead on your right hand, not the calculator, calculate the two results here.
Professor, the review for the exam will be on the 18th.
What is that?
The review for the exam will be on the 18th.
Yeah.
Thank you.
You don't want to wait till the 18th to
Yes, sir.
practice these equations. So in solving this, we're going to show the two parts that generate the quadratic equation here. So there's something I sub d plus a number times I sub d minus a number, some combination in there. And you have to determine the coefficient. Now, if you go back in this problem and put in the units, as I said, if you put the units in it, these numbers can come out to be much larger. However, it's all relative, basically, so even the numbers are larger, they still would equate. But we want to find out here, is there an error in this number 25? Should there be actually 26? And the only way, the best way to do that is to solve this quadratic, convert it to quadratic, and then solve it. do is, we'll give everyone an opportunity to solve this, independently. And then on our next session, basically you can present what your results are, and then you can we'll compare them to the results here, mathematically. If your results are different from the Arthur's results here, you know, I guess it's one of two reasons that they're different. And that's why I was saying something in this equation may not be okay. The 25 might be the 26. And just kind of go through the amount of time that it takes you to solve this by hand. As I said, a calculator will not help. It'll be obvious on the exam when a calculator was used. And for a final exam, only 4 function calculators are used. And that means no programmable functions are allowed to be brought up on your calculator. Our TA, Sheriff, is a graduate student, and he's very aware of when the calculator has been used to actually solve problems, especially quadrant math type problems. So just be aware that if you're interrupted during the final exam because he suspects some use of the calculator, be aware that no programming on the calculator, only 4 functions, and then that's why when you solve questions like this quadratic equation, it's going to take a few minutes, and you're definitely going to be writing several lines of math to arrive at a result. So we don't want any misunderstandings or surprises because of that. All right, we'll continue this at our next session, so we'll work on this, and then we'll go over your results.
Just 20 year repeater. It's 20 year repeater, 0.5.